Hi everybody. In this episode we are going to code a clock, an analog visual clock in C. It might be quite simple, but there is some trickery and magic going on under the hood, and we will explore all of it in detail. So after watching this episode, you will know exactly how computers track time. You will know exactly how to visualize stuff in pure C, and you will be better than before watching this video, obviously. So at the end of this episode, we're going to have an analog clock on the screen, a visual application written in C. All right. So first of all, we're going to need the time method. It's a standard C library method to get the current time in seconds. And in computers, time is a number of seconds since an epoch. And that epoch is, on most systems, at least in UTC time, it's 1970, 1st of January at midnight. So computers don't know absolute time. Just like humans don't know absolute time. There is no absolute time. There is no 2030. There's no year such as 2030 or 2040. It doesn't exist. It's always 2030 years past some event. Right? And in computers, that event happened in 1970. In human everyday life, that event is the birth of Christ, or in other regions, it's the birth of someone else. I don't care. Okay, so we always have a reference time, and we fetch the time in seconds from that reference time. So let's just create a new directory. And I'll call the source file clock.c. Let's include standard IO as always. Let's also include time.h. Why do we include that? We include that because in the time manual, it tells us to. And then we can, in the main method, already ask the system to give us a time as the number of seconds since epoch. We get that by passing in a time t pointer here. That can be null, as this documentation says. This is just a pointer to some time variable, and then the method will fill that memory space with the given time value. So this method seems to return the time in two ways. First, it accepts a time pointer here, and it also returns the time. So that means we can effectively just do time null, and we can store the results in a time t variable that's called now. And then we can use man to local time or man local time. Oh, and this is a library functions manual, as you can see, with a couple of time methods here. And this is also defined via time.h. And here we have a couple of methods such as ctime. This has nothing to do with C, by the way. This stands for calendar time, I think. Or ASCII time, character time, something like that. It does not have anything to do with the C language. So we can just pass a time pointer into that method. Let's just do that. ctime now, and that returns a character pointer now string, and then we can print that to the console. Now is a string, just like that. Now string. And let's see what happens if we compile this. If we compile this, then we should have already a working time. Let's see, analog clock, GCC. Let's enable all warnings because that's always super important. And then we compile the clock.c file. And now there is an error because I missed putting a semicolon here. Let's see if it's resolved now. Now we got a couple of warnings. Let's read them. Warning: passing argument 1 of ctime makes pointer from integer without a cast. Right, and that is because I passed into the ctime method, which expects a pointer to a time variable. As you can see here, this is a pointer. I passed a regular variable value. So we have to do address of now. Okay, now it should be good. And let's check what happens if we execute clock. And as you can see, we have the current time visualized, just like that. And why is this printing 2001? That's because I'd artificially just set my clock to some different value just for the sake of this video. I don't want this to time out in the future. I don't want this to be outdated in the future. So I just set it so I just set my computer time to 2001 for it to be blatantly obvious that this is not the real current time. Now we are printing the current time, and now we want an analog clock. We have the current time as a string, and we have the current time as a seconds value here, time t. By the way, time t is on most systems just a long, so it's just a 64-bit number. Now we can just visualize this in raylib using some geometry. Let's include, or let's just check raylib. So raylib is the library I'm using for graphical representations. It's super awesome. I can highly recommend it. If you want to learn it, just check out the other videos on my channel or just follow this very closely. So yeah, this will be good enough for learning it, definitely. So we include raylib.h, then this is the main method. This is, by the way, the basic example for raylib on raylib's GitHub page. We can create a window, and then there's this loop that we run. Let's go through it one by one in a second. So we create a window that has a width and a height. Width and height. And the text on that window, or the title of that window, is called, let's call it Daniel analog clock. And now let's define a width and a height, and then we can lowercase those here such that we use those global constants. All right. And if we compile this, it won't work because we have to link raylib. So that's the error we're currently seeing. The compiler tells us that the functions that we're calling, init window, begin drawing, clear background, etc., they are undefined references. The simplest fix to resolve that is to just append -l raylib, and this will get it to compile. All right, and now we have this window here. Daniel analog clock is printed in a faint font. We can just fix that, or we can remove this text since we actually don't even need it. But let's just print it in a sky blue and make the background black. And then compile and execute, and now we have a black window with a sky blue font. Okay, so what is a analog clock? An analog clock consists of a big hand, that's the minute hand, that's a hand that points at the current minute value. And I actually understand why clocks are hard to read for some people. And because this is pointing at the minute value, but this is pointing at 10 right here. And 10 is not the minute value at that position. At that position, that is 50 minutes. This is the small hand, that's the hour hand. So these numbers here are the hours. If it points at the 2, then that's hour number 2. And then that's the second hand down here. So we're going to basically just draw a circle with a small hand, a big hand, and a second hand. I will call them hour hand, minute hand, and second hand for second hand. Second hand. Yeah, like seconds, not like second choice or something. So basically it's just a circle with hands pointing at numbers. So the first thing that we need to do is draw a circle. How can we do that? Let's look at the raylib cheat sheet, or maybe even better, let's open raylib in my local system, user include raylib.h, here it is. And we want to draw a circle right here. So there's a function draw circle. We can draw a circle at center X, center Y, radius, color. And I would say, so when we begin drawing. Here we clear the background, and after clearing the background, let's draw a circle. Let's draw a circle like this, and the circle takes as arguments center X, center Y. So basically we draw it at the center of the screen. That's why X is width divided by 2, height is height divided by 2, Y is height divided by 2. Radius is, yeah, what's the radius? Maybe height. Maybe it's 50% of the height or something. Well, which is the same as height divided by, no, it's not height. No, that should be the diameter. Maybe let's do height divided by 4. This is, by the way, arbitrary. I'm just thinking of which values could be reasonable. You can, of course, do anything you like here. And and this, I don't know if this really works. So this is the radius. Radius, as you can see here, is a floating point number. That it means it can accept, it supports decimal places, and these are integers. So if we divide those by 4, this works by accident because these are big integers that are divisible by 4 without a remainder. And yeah, but we would have to be careful if we divided small integers by something and get a floating point number as an output, because that would usually return something with a rounding error. All right, but let's forget about that. I think that works just fine because those are big integers. And then a color. For colors, it's always quite nice to look up raylib colors, and there's a nice color palette online. Those are colors that are supported out of the box, and I think they are good enough for our small programs. Of course, you can define your own colors as well. If you look at color, that should be a structure. Yeah, right. This right here, this portion of the definition is basically a color structure. This is the structure, and it's cast to color, and it's an RGB color with an alpha channel. So that's the opacity. So which color can we pick here? I would say let's just pick a white or a ray white. Ray white color. Ray white, by the way, what's the point of ray white and sky blue and dark gray and light gray? All those colors. Why don't we just use white? As you can see here, this is not exactly white. White would be 255, 255, 255. So all values maxed out. That is perfect white. Perfect white is if every color value in RGB, red, green, blue, of a pixel is maxed out. If every color is turned up at the highest brightness. That is quite cumbersome for the eyes. It's quite straining. So that's why many color palettes use a reduced white. And in this case, it's ray white. And as you can see, instead of defining RGB with 255, it's using 245, which is a bit nicer on the eyes. You won't even visually perceive the difference, but it is nicer. You will feel it on your eyes. And I find that this is still quite white. Okay. So 2 fixes. I will remove the text and I will increase the diameter. Maybe let's make it height and then this. Okay, so this seems to be a nice size for our project, in my opinion. We can also reduce the width to 600 as well. All right, so this is now a small graphical application with a clock. Now comes the fun part, guys. And that fun part is drawing the individual tick marks on that clock. Yeah, something like this clock here, where you have these tick marks, these minute marks on the watch face. So I will create a method here that's called void, because it returns nothing. Draw minute markers. And we're going to draw minute markers. We don't even need arguments because they're always the same. They just depend on the width and the height of the screen. Or maybe they depend on the radius of the clock, to be precise. So let's do, let's accept a radius, clock radius, yeah. And that should be it, because all we need is the radius of the clock, and then we can draw those minute markers around the edge of the clock. And how do we position those? That's not as straightforward as you might think, because it involves quite some geometry. So we have a clock. Oh, that's a horrible clock. Oh my God. Let's just say this is a clock. It's a potato clock. And then we draw the first minute marker up here, then the second one there, then here one, then there, then there, then there, then there, then there, going around the clock. So the first one depends, or actually any marker depends on the center coordinate of the clock here. And then we have a radius of the clock. That's the radius r. And then we have an x. Oh, let's not look at the first one. That's a bad example. Let's look at a random one, such as this one. We still have a radius. Then we have an x component here. That's x. And we have a y component here. That's y. And the x component is equal to, if we check out this angle here. So as you know, a full turn around a circle is 360 degrees. And that means the angle difference between each tick mark is 360 divided by 60, because that means, because a hour has 60 minutes, that means between every tick mark there's a 6-degree difference. So yeah, okay, so that's good information already. And x is for the first mark. Let's just pick this color. For the first mark here, x is equal to 0, and then it increases. And whenever you think in circles and something starts at x equals 0, then that's a sine function, because a sine function also starts at 0, increases, decreases, and then goes back to 0. So whenever you see circle and something starting at 0 and then progressing, then that must be a 0 here, a sine wave. When you think of the y coordinate here, the y coordinate is currently the radius, so it's maxed out. That means the y coordinate must progress according to a cosine, somehow like that. Because cosine at angle 0 is 1. Okay, let's just try to do something. So we have a clock radius, and we multiply that radius with the sine of something. Let's include math.h. It should already be included via raylib as far as I remember. Math.h. Yeah, it probably is, but I don't know for sure. So we multiply that with the sine function of alpha, and then that return value is an integer. No, it's a floating point number. That's x. Same for y, but that is calculated according to cosine of f. Okay. And then we do something. By the way, I still have no idea how everything is going to work out at the end. I'm just thinking conceptually now. So geometry-wise, x is growing according to sinus and y is moving according to cosine. And then we need a counter for 60 minutes, starting at 0, while I is smaller than 60 minutes per hour, I++, and then we do something for every minute marker. Currently, we're probably correctly positioning X and Y. Let's just visualize that result. Draw a rectangle. Let's just draw rectangles at those X and Y positions with some width and a height and a color and just see the result. Draw rectangle at X and Y with some width and height. Let's just make it 4, 4 and some color. Let's make the color just red so we can easily see it. And then we just make sure that we call that function down here after draw circle, draw minute markers. And I will uppercase that function because I want it to be aligned with all the other functions that we call. Draw minute markers here. And it takes as input the clock radius. And the clock radius is a floating point number, clock radius, and it is height multiplied by 0.4. And then we replace this height multiplied by 0.4 with the clock radius. So this is just some small refactoring. Clock radius. Okay, and now we're calling the draw minute markers function inside this drawing loop. So as long as the application is running, we are drawing minute markers. Let's see. I've compiled. There's currently an error. Of course. Oh, damn it. And that error is the alpha angle, which I haven't even defined here. So let's define it. It's a floating point number. It starts at angle 0. And then it progresses somehow. So first we draw alpha at 0. Then alpha is incremented by 6 degrees, or if you want it to be more expressive, you can also type 360 divided by 60. So 360 degrees divided by 60. Oh, and this might not work because sine f is expecting an angle in radians. Let's just have a look. Sine f. Well, actually all sine functions, unless explicitly stated, will expect an angle in radians rather than degrees. So you could just multiply this with, I think, 2 multiplied by pi or something. Don't quite remember. But I know that in raylib there's a dec to rate constant here defined. Right, this one here. Dec to radians, which we have to define, which we can use to convert the angle, which is in degrees. So let's just make this explicit here. Angle is in degrees. Alpha degrees, alpha degrees, alpha degrees. And we convert that in the sine function to radians by multiplying it with dec to rad. And then we just increment alpha in degrees by 360 divided by 60, which will result in 6, but you can, whatever you prefer. I don't like magic numbers, so maybe this is more expressive. And people complaining about performance because this is computed with every iteration. No, it will not be computed with every iteration in this loop. Because this is something that the compiler will just see and optimize away. So the assembly or machine level instructions will not differ from defining a 6 there. So currently there is an undefined reference to symbol sine f. That is because we have to link math as well. So let's append -lm. And now it compiles, and let's see how the clock is running. And as you can see, it's somewhat working. We are drawing the minute markers, although they are positioned completely off the screen. And that absolutely makes sense because we are calculating x and y without an offset. So we have to move them toward the center of the screen. So let's just define as an input here a x center or center x center like this maybe, and a float y center. And then down here we are drawing a circle at an x center and a y center. That is width divided by 2 and height divided by 2, and we can just write them here. Now center and y center. Okay, let's see. There's now an error, too few arguments. Right, that's because we have missed, or I have missed, adding the arguments here as an input. Just like this. Or what we could also do is to just do something more raylib-like, and in raylib there's a structure defined that's called vector2. And this is a structure that allows us to store an x and a y coordinate inside this single structure. So we can just do vector2 center. So basically that's the center point now. And then instead of drawing minute markers like this, we can draw the minute markers like using a vector2, that's a center. Vector2 center, and it consists of x center and y center. And now we can reuse that center inside the draw circle vector method, because there's not just draw circle for circles with a center x and a center y coordinate, there's also draw circle vector. So here's draw circle v, and it takes as input a vector2 instead of center x and y values. So this one is very handy here to just keep the code concise. So let's use that one, and let's use that same center also for the draw minute markers function. I don't know if this compiles. It compiles. Okay, good. And now the minute markers are still drawn off center, obviously. So we could do, or we have to put or move the markers toward the center by just calling center.x plus this here and center.y plus this. And now, as you can see, we have a circle and we have minute markers around it. That means the positioning of the minute markers is correct. And now we just have to make them proper lines. Okay, but this is already showing that our implementation is working very well. So now I want the minute markers to not be well, currently they are just points on exactly the radius of the circle, which I don't want. I want lines right here. So this might be a bit more interesting, but we can find out how that works as well. So how do we do it? We define x and y. I know there's an interpolation method in raylib which we might use. So instead of drawing rectangles, now we want to draw a line based on a starting position and an end position. The starting position is, or might very well be, this x and y here. Let's just reduce the radius a bit. Let's just say, for example, multiplied by 0.9 or something like this, such that the markers are moved inside the clock. Right, so this looks good. And then I want the markers to extend toward the radius, toward the perimeter of the watch face. How do we do that? We just define an outer x and y. X outer, y outer. And then this might be the x inner and the y inner. And the outer X and Y might be at position, well, let's say 98% of the radius. Okay, and now we don't draw a rectangle, we instead draw a line based on vectors. So let's define a vector 2 here, inner, that consists of X inner and Y inner, not inter, but inner. And then we draw an outer, or we create an outer vector just like this. Outer. And save. And now we need to just draw it. So let's just check out the draw line function here. We use draw line v, which draws a line based on 2 vectors, so 2 coordinates, start position, end position, and color. Let's check out that one. Draw line v. Oh. Draw line v based on inner, outer, and a color. Well, the color is red. And now we have a proper watch face. What I don't like is that the lines are so thin, but that is of course natural when we are just drawing a line. There seems to be a drawLine X function based on start position, end position, and a thickness. Using GL lines. I don't know what GL lines are. Does this have anything to do with OpenGL? I don't know. In case it is OpenGL, probably it's not, but yeah, this is just some advanced expert functionality probably. Now let's just add a thickness value here. And let's just say the thickness is 3. And let's compile, and that doesn't work because of course I have to change the method call to X rather than vector. And I would say that one looks quite good. This is a proper watch face in my opinion. I would just say we should adapt the color to gray just to make it more neutral, because the hours and minutes and seconds hands should have the focus, and this looks very good so far. Okay, so we are drawing minute markers now. Let's draw the hour hand. And drawing the hour hand, what does the hour hand need as input? It needs as input the center, maybe its length. So let's define the hour hand or hour hand length. And that length is, let's say, that length is, and we can also just define the radius globally if we do that. Clock radius is this. It's also a constant, then a constant float hour hand length, and that is clock radius. Let's say it's half of the clock radius. Yeah, that looks good. And then we draw an hour hand based on that. So all we need to know is the center coordinate, although the center can also be globally defined. Const. All of those are perfectly valid global constants because they never changed. They are just properties about the geometry of the clock. And then this is the hour hand length. Let's also make a minute hand length. That is, the minute hand is always longer, so let's make it maybe 80% of the clock radius. And then the second hand length, oh, maybe the second hand length should be 80% of the clock radius, while the minute hand length should be, let's say, 65% of the length, and the hour hand might be 40%. I think that might work out. So we draw the hour hand first. And now comes the fun part, because the hour hand position depends on the time. It depends on the current time. So in that time function or local time, somewhere here, there should be something. Right, the local time is taking as input the current time in seconds and returns a structure tm. And that structure is a broken down time representation. Here it's a broken down time representation such that we can access the seconds and hours and minutes of the current time as far as I know. Struct tm. So it should take as input. Yeah, let's just have a look online. See local time. Let's just search for local time hours. Yeah, you can use the local time function here. We get the current time, and then we break down the time using the structure tm. And we can access tm year, tm month, tm day, hour, minutes, seconds. Okay, so it seems to be quite simple. So here we get the C time, which we don't even need anymore. I'll just leave it in just for fun. But what matters is that we get the structure tm, which is the time. It's basically a formatted breakdown of the time. And struct tm is, let's just call it t, and that is local time of now. Yeah. Okay, so this is the local time, which formats this structure here. And then we pass that structure t here, or that structure pointer here. And this is then drawing the hour hand. So let's define the method here. Draw hour hand, and it takes as input the center, although the center is a constant. So let's remove it in all those methods here. And the clock radius is also a constant. Draw minute markers, doesn't need any arguments. Draw hour hand just needs the time argument, the current time. And yeah, so it takes as input a struct tm pointer t, and then it uses a very similar mechanism as this one to draw a line that represents the hour hand. So let's just copy this. I mean, it will probably be super similar. So we have an inner x. Basically, the inner x is the center x. So vector 2 inner is actually the center vector, which we have already globally defined up here, because the hour hand obviously starts at the center of the screen. So we can just draw a line from center to the outer coordinate. And the outer coordinate is the clock radius multiplied by it's not the clock radius, it's the hour hand length multiplied by sine f, etc. Then this is also hour hand length multiplied by cosine of this. And then this outer coordinate is set here. And the magic is now, how do we determine properly the alpha in degrees? That's the magic of this function. So the alpha angle is equal to the time currently, and we get the hours. Let's have a look here. TM hour. And this returns, the hour currently, of course. And how do we derive the angle from the hour, well, hour 12? Oh, damn it. So one thing that we have to do is probably modulo the hour by 12 or by 13, because an analog clock wraps around after 12. So we have to also wrap around the hour values. What if the hour is 14 or 16? And we have to wrap around after 12. Let's just do it super simply. This is just embarrassing otherwise. So we have a clock. Let's say this is the clock. This is our 0, this is our 1, this is our 2, this is our 3. Here, for our 0, the degrees are, this is the alpha, 0. For our 1, the degrees are, well, for our 3, it's 90 degrees. For 1, it's maybe 33. Ah, no, it's 30 degrees, of course. And then for our 2, it's 60 degrees. It's so simple. We simply do multiplied by 30 degrees per hour. Oh my god, if that's the solution, I feel stupid. Ah, so for hour 15, the current alpha in degrees is 60. That is, of course, not correct. Why? Because it's divided by 13, which is wrong. It's divided by 13 and then the leftover is taken. What if we divide by 12? Ah, of course, we have to divide by 12. Okay, we figured it out. It was super simple. I was just... All right, so the alpha in degrees is simply the current hour divided by 12, left over because it wraps around after 12, and then we multiply by 30 degrees per hour, because 1 hour just increases the time, the pointer, by 30 degrees. But then additionally, the hour hand position also depends on the minute and second values. So because the hour hand interpolates also between times, so it can just as well point between the 1 and 2 if the minute hand is some value pointing down here, for example, at 30 minutes. So we have to also consider this minute alpha add-on is equal to, and let's get from the TM minutes, we will divide that by 60 minutes per hour. Okay, this is always a value between 0 and 60. We divide it by 60, of course. So that's the percentage progress. And then we know that the alpha in degrees must add on 30 multiplied by minute alpha add on or minute alpha progress. So this is a value 0 to 100% of an hour complete. And then we say we know that an hour has this many degrees, and we just interpolate 0 and 100. Oh, let's try. TM minutes. What's wrong with that? Ah, TM min. It's TM min. And then minute alpha add-on is undeclared. Ah, right, because I have to change it to progress. Okay, this looks okay-ish, but we have to add to the degrees the minute alpha progress. What is currently the value here? Because normally it should point beyond hour 3 currently, but it's pointing above it. So that's what's confusing me right now. Maybe I have to just make sure that this is a floating point number. know that what was implicitly cast by this. And here the current alpha in degrees is calculated to be 95. But why? One thing that we always have to do is we have to refresh the local time for each iteration here. So let's do that. Local time now, and now is equal to time null. And we can do that outside of the drawing loop, of course. And that returns the value of this structure struct tmt is equal to local time now. But something seems to still be wrong. We're drawing the hour hand here. Let's just make sure that there are no warnings. Yes, there are no warnings currently. Minute alpha progress. So we check how many minutes have progressed in the current hour. We divide it by 60, and this gives us a percentage progress. And then we add 30 degrees multiplied with that percentage progress and add it on top of the current hour. This is probably the last question that we have to solve before we are completely done here. Plus 30 multiplied by minute alpha progress. Let's just do the following. I will just change this compilation command to include the debugger flag. And now let's debug this. Let's not just try to solve it by thinking. That's not always the most productive way to do that. So we can just call gdb clock and see what happens inside this function up here. So we put a breakpoint in line 19, for example, and run the application, fix up the layout. Oh god, this is very hard to read. But we can see that we are currently breaking, the breakpoint is triggered in the current alpha degrees computation, but I'm interested in the minute alpha progress. And it's 0.21. That means 21% of the current hour have been completed. So this sounds to me as if it were correct. If we continue now and then print that same value again, continue. Yeah, okay. So here it seems that this value is slowly changing, which makes sense since the time is passing. However, so that means, oh, I think it's the same issue that we encountered before. It's just that we have to reduce. Do we have to reduce the progress by this amount? And this looks reasonable now. Yeah, the issue is that the coordinate system is pointing down in graphics, and that's what's so confusing, and that's what I am messing up here. So this required a minus, right? Because the angle is measured starting at the bottom of the screen. But this also means I would be inclined to even do a coordinate transformation such that this angle here, this is alpha, such that it is a regular alpha aligned with the x-axis. So we can do, or well, we can either do that, or we can just think, we can just adapt our thinking. So currently the hour is this, we multiply by 30, and then we, yeah, this is flawed, or this is risky, because currently we are executing the application at 15 o'clock. That means there's risk that at different times, which I just can't test right now, something is broken. I actually, ideally, in an ideal world, no, I want the hour, I want the angle to be 0 when it's pointing up. I want this to be angle 0, just like time 0. This would be most convenient. To do that, how do we do it? I think we just have to do minus 180 to flip the angle. And definitely we have to progress the angle by 30 minutes multiplied by minute alpha progress. This cannot be a minus, that doesn't make sense. So this is the alpha degrees currently in relation to the 0 angle. The 0 angle, however, is located somewhere we don't want it to be located at. I think even the clock is running in the wrong direction because y is flipped, but x is not flipped. Ah, this is so weird. So we have to do alpha degrees is this. But when printing, we have to center x this, center y this, but then maybe minus for the y coordinate. Maybe that's it. I'll compile and execute the clock. And this is it. Okay, so I just had to flip the y coordinate right here. So that was the magic. Now this computation here for the degrees is correct. That's awesome. Okay, now we have a working hour hand. And unfortunately, of course, hours are progressing so slowly that we can't really see it moving, but it should be moving at an ultra slow speed. All right, but now we have the magic code completed, just that we just have to extend to the second and minute hand visualizations. So what we need to do now is just create a similar method called void draw minute hand, also based on the struct tm time, the current time. And it's going to be super similar. Let's just copy this code up here. Minute alpha progress, and we just make a second alpha progress here to also transition the minute pointer in relation to the second pointer. So this is going to be depending on seconds. And we also have 60 seconds in a minute. And then we have an alpha degrees that depends, instead of the hour, on the minute, divided by 60, multiplied by how many degrees do we have per minute? We just have 360 divided by 60 degrees per minute. So we will have to do this. I'll just hack it all together now. And then the visualization depends on the minute hand length. Minute hand length like this. Minute hand length. And that should be it. The thickness of the minute pointer maybe should be like something like 6. And I will just pick a different color here in the raylib color palette. For example, we used red for the hour hand. Let's use blue for the minute hand. Blue. And then let's call that method down here. Draw minute hand. Compile. Oops. Minute alpha progress. There's an error with that. Of course, I need to adapt this to second alpha progress here. And this compiles, and now we have a clock, and it looks like this is the actual time that is currently set in my system. Why? How do I even get the current system time? Get current time in bash. Never really fetched the current time in bash, by the way. You can use the date command. Okay, so let's use the date command. Date. And currently it's 3:25 and 25 seconds. And the application that's running tells us it's currently 3:25. That makes sense. That looks correct. Okay. And by the way, I have the feeling that in the clock, every hour marker should be a bit longer than the minute markers. That would be a bit easier to read. So let's draw the minute markers, but instead, but here we check. if I equals, or if I is divisible by, we have 12 hours, so by 12 probably. No. By 5, every 5th minute is a longer marker, as far as I remember. If this equals 0, then we draw a line, else we also draw a line, but the thickness is just different. So it could also be a single statement, but we check here I modulo 5 equals 0, question mark. If yes, then the thickness is, or the thickness, this is the thickness, I want the length to change. Oh, damn it. How do I change the length? The length must depend on, that's the length right here, this 98 thingy. Okay, so, no, that's the length, because that's the inner part of the coordinate. Then let's create a variable outer position percentage, and that is 0.98, and replace this here and here, and then the float inner position percentage is equal to 0.98 minus and then we ask, is I equal, or is I modulo 5 equal to 0? Then we do minus 0.12 maybe, else we do minus 0.08, and then we do inner position percentage here. Okay. Yes, and I can even see the minute marker moving right now. This is awesome. Seems to be working. Wait, I didn't see the minute marker moving. I meant the minute markers here are longer. Perfect. Awesome. And then this minute hand is slowly moving. You can see it by the small pixel shifts there if you look very, very closely. And now let's draw a second hand. And the second hand behaves a bit differently because it does not move continuously like the other two hands, but it moves in sharp steps. So we don't need the second alpha progress. We just need an alpha in degrees, and it depends on the second value. No modulo. By the way, the minute hand doesn't need a modulo either. Yeah, because it always wraps around, of course. So we can remove that. And then this second value here is multiplied with 1 degree, because every second is just 1 degree. So we can also leave out that 1 degree per second. No, a second is not 1 degree. A second is 360 divided by 6 degrees, of course. Yeah, so basically it's 6 multiplied by 6 degrees. And then that's the second hand length here, second hand length there, alpha in degrees, x outer, and the thickness is, let's say, 2. 2 pixels, and the color is yellow? Nah, gold. Let's make it gold. I'm not sure if that will look good. Or actually, I prefer something like lime or green. Let's do it lime. Draw minute hand redefinition. What's going on here? Ah, right. I need to fix that up to a draw. Draw second hand. And this is not working because I haven't called it down here, of course. Draw second hand. And now let's see what's going on. And now that's a working clock, guys. Awesome. Is there anything else we need to check? Yes, there's one more thing we need to fix up because this is currently running at an infinite frames per second. So let's set a target FPS to 60 frames per second. We don't need any more than that. Otherwise, it will run at 5,000 frames per second or something like that, which we definitely don't need. And now let's check. This is now the compiled program. This is the clock. And this is the result of this episode. Guys, if you want to learn C from scratch, real practical C, not the bullshit academic slop C that is taught in all the courses everywhere, then have a look at the description down below. I have created a no-nonsense C programming course which only focuses on practical C programming skills. And what it will definitely do is save you a ton of time because it has a structured learning path that gets you from knowing nothing about C to practical C skills in a linear, progressive fashion, no time wasted. All right, if you enjoyed this video, then I hope to see you next time. Bye-bye.